Now, as we all know, Camunda 8 introduces powerful capabilities, but its event-driven and eventually consistent architecture also brings new challenges. And to navigate these challenges and provide a practical toolkit to improve the robustness and reliability of your C8 applications, please join me in welcoming Josh Wulf to the stage. Josh.
Thanks, Kevin.
Welcome.
Welcome. I'm not sure what the last title said. This one says Writing Reliable Camunda 8 Applications. I don't really know what this presentation should be called, but we're just going to do it.
Patterns to use today to make C8 apps even more reliable.
Okay, that's it, yeah. The actual title that I submitted was Camunda 8, The Missing Parts. But most of those missing parts got created and put into the product before we're launching it next week. So I'm standing on the shoulders of giants here, following Alex and Toby and the great work they've been doing. My name is Josh Wulf. I'm a developer experience engineer at Camunda. I've been with Camunda since 2018. And before I joined Camunda, I wrote and open sourced the Node.js client for ZB at the time, and I've continued to work on that for the last 7 years. So I'm deeply in the SDK development space. So the team that I'm part of, Camunda Experience, we're leading the development of the Polyglot SDK experience, and our team takes care of the last mile from our engine to your application. So our code is Camunda code that is in your application running inside your business domain. So our mission is to provide first-class IDE and build chain support for writing provably reliable applications in multiple programming languages with Camunda 8. And my spell checker was complaining about the word provably reliable. But what that means is that they're not just like, I guess it's reliable, but you can actually prove statically that it's reliable, which means your build chain can fail deployments if the application is unreliable. So some of the principles in the design: first-class support for system characteristics. Some of the ones that Kevin mentioned: eventual consistency, distributed systems, so that you can focus on your business logic rather than learning about the quirks of the system. Early explicit failure. It's one of our principles that we follow. And it is, again, Camunda code in your application. And then some of what I'm going to be demonstrating to you today is this idea of a Camunda engineer in your IDE. Basically, the idea is that if a Camunda engineer sitting next to you while you're coding can look at your code and say, that's not going to work, then your IDE should tell you that. And so with these new SDKs, that's what we're bringing to the table. So our goals: we want to scale, and we want to scale your business and our business as well, obviously. We want to scale code bases, more code, more types of code, more languages, scale development teams, so you can add more developers to your team, including agents, AI coding, and scale processes. So more process instances and more process definitions, so you can bring more and more core business processes onto the engine. So the basis of all of this work that we're doing now, you might have seen in this morning's keynote that we're going to be releasing a Python and a C# SDK. It's all building on top of this Camunda 8 public API REST specification that Toby pointed to in the last presentation. It's a compile time guarantee of predictable runtime interoperability for systems that correctly implement the specification. So we generate out of this specification, including like a comprehensive test suite with thousands of tests in it, for us to test the compliance of our own system. And then we provide through our SDKs the ability for you to test the compliance of your client application, and then the two of them meet at runtime, and they run as a single integrated system in your business domain. So here are 3 of the challenges in Camunda 8 that I wanted to discuss with you today and show you how we address them in the new SDKs. Eventual consistency, distributed systems, and runtime type safety. So let's have a look at the first one, eventual consistency. This is the architecture diagram of Camunda 8, the latest one from the new documentation. And it shows all the different kind of components. And it's kind of a consulting answer to say it depends, but how you draw the system depends on what you're interested in. So I'm going to go back to an older diagram, which is now out of date, but it focuses on the part of the system that I want to talk about today. So here we see the clients and the job workers, your application running on the left-hand side of the screen, and then there's the ZB cluster, the orchestration cluster, Camunda 8. It's got a gateway in front of it, it's got brokers in it, and then there's the secondary data storage out the back where it says Elasticsearch, but we also support RDBMS coming soon. So eventual consistency. Some of the operations are backed by strongly consistent data, and some of the operations that you perform are backed by eventually consistent data. And so the challenges with that are, when you're programming, you're developing an application, well, which ones are strongly and which ones are eventually consistent, and what does that mean? Like what's the actual implications for my application? So I think in my original pitch, I said that these were going to be some ideas from CQRS systems, command query responsibility segregation. We have a read channel and a write channel. And this system wasn't formally designed or designated as a CQRS system, but in working with it over the last 7 years, I found that if you think of it as CQRS, 80% of the time you're going to be using the right mental model, and the other 20% of the time you're going to run into problems. But we'll do the 80-20 rule here. So basically, you send all of your requests to the REST gateway, and then some of those requests go to the engine, and those are the strongly consistent ones, and some of them go to the secondary storage, and those are the eventually consistent ones. So command operations, you can think of it like this. Command operations are strongly consistent. Query operations are going to be eventually consistent. So generating the documentation from the specification, as Toby pointed out, enables us to clearly mark each of the endpoints with its consistency. So the green one there is strongly consistent. The orange one is eventually consistent. So I create a process instance, strongly consistent. I get the process instance, eventually consistent. So I think I've got a demo. Yeah, let's do a demo. Okay, hopefully you can see this font there. This is just a shell script that deploys a process, gets the process definition key, creates a process instance, and then immediately gets the process instance using the key that it got back from the creation. So if I run this little demo here, CamundaCon eventual shell. So you see here that it creates the process instance, it gets back the process instance key, and then I say, okay, give me the process instance then, and it says 404, it's not found, like it doesn't exist. That's because the get process instance endpoint is eventually consistent. It's counterintuitive, right? I know the process instance exists, and I only know it exists because you just gave me a key, but when I ask you for it, you tell me that it doesn't exist. Like, what is going on here? I'm confused. How long does this take to become consistent? Well, it depends. I'm not in consulting, I'm in engineering, but it does depend. It depends on the system load, it depends on the time of the day, the alignment of the planets. There are so many things that it depends on. So let me show you how we do this using one of the new SDKs. So this is a new generated SDK for Node.js and for browser. So it runs in the browser. That's another feature that we get with a fully featured REST API now, because you can't do gRPC in the browser, but you can do REST. So we're doing the same thing. We create a Camunda client. We deploy the model, and then we create a process instance, and then we get the process instance. So let me run that. SDK. So we can see again, we created the process instance with this key, and then it came back and said that it's not found, 404. So exactly the same thing. Now, since this SDK is generated out of the specification, just like the documentation has awareness of which endpoints are eventually and strongly consistent, the SDK does as well. So if you can see that tooltip hint, it says at the bottom, consistency, eventual. This endpoint is backed by data that's eventually consistent with the system state. So if I comment out this line here, you'll see that my IDE starts to complain because it says an argument for consistency management was not provided. So what we do is we surface the eventually consistent nature of any of the endpoints in your IDE, and we have you confront what that means and what you want to do about it. So you have to make a statement about what's your tolerance. Like, if you don't care if it's there or not right now, you just leave it set to 0. But I'm going to set it to 10 seconds. I'm going to give it a 10-second tolerance. It doesn't mean it will take 10 seconds, but it will wait for up to 10 seconds for the consistency to settle. And if I run it again, it now returns my process instance when it's ready. And if I run it in trace mode, so I can get some additional information during development about the behavior and performance of my system, it tells me here that the elapsed time to retrieve that was 4.6 seconds. This is on an unloaded system running on my local machine. Now, there are many situations where you don't care about the eventual consistency, but even now we're encountering things, especially with agentic AI. We don't discriminate at Camunda. We equal rights for silicon intelligence. So when AIs and AI agents are using our system, they have a faster response time than humans, and we don't discriminate against that. We give them the opportunity and the ability to do it. The other thing is that when AI agents are writing your code, they're not going to write code that runs fine in the development, and you're new developers. They're not going to write code that runs fine in the development environment, but when you put it into production and it goes under load, suddenly it starts failing in random, non-deterministic ways. So this, you can even set rules, for your business rules for your developers about how they handle eventual consistency. So that's how we deal with eventual consistency. Okay, the next one is distributed system. So this is a distributed system. You can see even inside the system it says it's distributed, but then it's also distributed outside because you have your job workers that are talking to the broker, and no one really has the full picture of what the system load is. So who was here in the Walmart talk earlier today, where those guys were talking about using the adaptive backpressure algorithm to get their system load working. So load is distributed in the system, and the challenges are that scaling can be counterintuitive, because you can think that if I add more workers, it's going to speed things up, but it can actually slow things down even further, because activate jobs is actually a command, and every time you issue a command to the system, it puts more load on the system because the stream processor needs to process it. So more workers actually equals more work for the system. So with this new SDK approach, and this is some of the design thinking that informs not just the Node.js SDK, but also our Python and C# SDKs that are coming, has distributed adaptive load balancing via backpressure. So the client sends a request, activate jobs, or create process instance, and if the broker is under too much load, it sends back a backpressure signal. Now, for the last 7 years in the Node client, we've had this naive approach to client backpressure because it's an exception, and it's an exception that gets thrown, and the Walmart guys, from the way they described it, they said that they're just dropping the request. It's an exception, it blows up, it goes away. But usually, if you're asking the engine to do something, it's something that's important in your business and that you want the engine to do, so you're going to back off and then retry. So we made that just transparent in the SDK. It just backs off and retries automatically. It doesn't throw an exception. And so it'll make a call, it'll get a backpressure response, and then it'll back off and retry. Then, in your application, you make some other call, it gets backpressure, and it'll retry as well. And so that repeats like that. So the application doesn't fail. It backs off and tries to reduce the load on the system, so eventually it recovers and it continues. But it's a naive approach because the backpressure awareness is scoped to each individual call. So with this new adaptive client backpressure, the way we do it is when we get the backpressure signal, the SDK maintains a backpressure status of the cluster. And so subsequent calls, while the cluster is in the backpressure state, start to back off immediately, so the initial call doesn't happen. As soon as the earlier calls complete, then subsequent calls are made immediately. So I'm going to give you a demo here where we're going to start 1,000 processes every 3 milliseconds. Each process has a 50 kilobyte variable payload, and we're going to have a worker that's going to try to complete one job every 3 milliseconds. npm run, CamundaCon, backpressure, legacy. Yeah. Okay, so yeah, it's going to start. You can see it's starting processes, and you see there it says backpressure equals severe. So the system is under severe load right now. Actually, if we go to the Docker logs, they're pretty small. Can I make them bigger? Oh, yeah. It's just throwing tons of these resource-exhausted exceptions on the server. Okay, completed. It took it 29 seconds to complete doing that. And so now with like 0 code changes, I'll just show you the code here. Backpressure. So the only code change, it's not a code change, it's an environment variable. You just change the Camunda SDK backpressure profile. So I'll turn on the client-side adaptive backpressure management. So if I run it with balanced, it's called. Exactly the same scenario, except now the client is backpressure status aware. And you can see the backpressure is healthy. So it would have spiked at the beginning, figured out what was happening, and it completed the same thing in 9 seconds. So I ran, who missed the Walmart demo and went to the Brazilian Globo scaling talk next door? Anyone went to that? Yeah, you were there? So they were talking about running 10,000 process instances per minute. They do like 30 million process instances a year. So earlier today, because it would take too long to do it here, I ran a 10,000 process instance using the legacy backpressure. So the system doesn't fail, it doesn't fall over, it just really slows down. So you can see here in the first one, the process instance creation per second, there's a big boulder of process instance creation, and it's kind of squashed because the system is under load. And then the process instance completion per second is like flatlined, and then once the creation pressure comes off, the throughput starts at that point. So, you know, if you drew a vertical line up from the beginning to the end of that peak there, that's 29 seconds. Or in this case, it took 4 minutes and 21 seconds. I just turn on the adaptive backpressure, and it takes 43.2 seconds. And you can see it's just this big kind of spike of throughput. So that's how you can do adaptive backpressure management in the client. What's next? Runtime type safety. So the specifications are compile time guarantee of predictable runtime interoperability for systems that correctly implement the specification. And what the SDK does in your IDE and in your build chain is it proves the compliance of your system with the specification. So I got a demo for that. Let's go here. Tags. Yeah, so a new feature in 8.8 is tags. You can tag process instances with different tags. Maybe you don't have multi-tenancy, maybe you're running in SaaS, but you want to segment your workloads by some dimension. You can tag your processes, and you can search for them using the tags. So here we just create a Camunda client, deploy a process model. We create a process instance, give it a tag, some tag, you know, by process definition key. Create one, and then we create another one with another tag. So let's run this application and see what happens. This is CamundaCon, tags first. Okay, so it made the call to the broker, and then the broker responded with invalid argument. The provided process definition key test process is not a valid key. Expected a numeric value. Did you pass an entity ID instead of an entity key? This is how this whole journey started. I watched Copilot writing an application using the Node.js SDK, and it made exactly this mistake. And I couldn't understand the message that came back from the server, so I contributed a patch that patched it with a message that tells you kind of what you did wrong. But then I was like, oh, that's monkey patching this whole thing. So what I've done here is I've actually imported a loose client. It's not a strongly typed client. If I change that to the strongly typed client, which is the default, you can opt out by importing the loose client. Or it actually has a feature where it checks the name of the currently logged in user, and if it's Chuck Norris, it turns off all the type safety automatically. Otherwise, it's on for everyone else. So you can see here that it's indicating, this is the Camunda engineer looking over your shoulder going, that's not going to work. Why? Because I've passed a process definition ID value in a process definition key field. So these fields are now type disjoint in the IDE and in the build chain. So those kind of beginner errors, they don't happen anymore. And my error is here. I put the process definition ID into the process definition key by mistake. So if I change that, that fixes that problem. Okay, I'm going to turn off my type safety again to demonstrate the next one. So I fix that, and then I run it again. The first process instance creates fine. There's a tagged process instance in there. Press the key to continue. The second one blows up. Invalid argument. The provided tag hash some other tag is not valid. Tags must start with a letter, followed by alphanumerics, underscores, etc. It cannot be blank, and it must be 100 characters or less. So the problem here is that my second tag is actually invalid. Now, catching this, if you're programming in Haskell or Scala, then we can catch this in your IDE, but we can't do that for languages like Java, C#, and TypeScript. So the way that we've dealt with this is we disallow free strings and require you to lift them into specific types. So you see here it says that you can't use a string where a tag is necessary. So in this second one here, I create the tag, I use tag from string. And you can see I've got the constraints in my IDE, it's telling me, but it still can't validate the tag at compile time, or at design time in my IDE. But when I run this one, this is what happens. Second. Creates the first one, and then the second one blows up. But this time, instead of blowing up during the call to the broker, it blew up on the client. And it told me that the tag's invalid, and it gives me the constraint pattern here. So that doesn't seem like much of a difference or an advancement, like, okay, it still blows up midway through. Now you're just blowing up on the client instead of blowing up on the server. But if you think about it a little bit differently, if you treat the type system as an I/O boundary, because that's what this is your I/O boundary, and during an I/O side effect operation, the application is blown up. So if we treat I/O operations as a first-class concern, and then we coalesce them, and then we move them to the edges of the application. So what we can do here is we move it to the beginning of the application lifecycle into the startup. So in this third one here, rather than creating those tags in line, we hydrate the tags from some configuration on disk or wherever we get them from, and then we create them, lift them into the tag type. And so you can see this application has a setup stage, and then it runs the main stage. So if I now run this third one, my application blows up before it starts. It doesn't blow up in the middle of some business transaction. There's no business logic. There's nothing happening. The application won't even start. So we took an application that works 100% of the time, 50% of the time, and turned it into an application that predictably and reliably refuses to even start because it contains a code path that we know will blow up at runtime. So we're giving as many tools as we can, and some of it's going to require how you architect your applications to make them reliable and predictable, which includes having predictable failure modes. So yeah, we want you to be focused on solving your business problems and not technical implementation details. We want you to be able to write provable code that's resistant to unsafe refactoring. Those kinds of IDE errors you saw for wrong type fields and those kind of things, you bring someone new into your organization or you go back to some code that you wrote 6 months ago, you want your IDE and your build chain to be able to stop you from making changes that are going to break functionality that's already existing and working. We want you to be able to add new developers who don't need advanced knowledge. And we want more and more core business processes running on the engine. So what's next is the Python SDK and the C# SDK following in this same kind of design philosophy. Thank you.
Thank you, Josh. And thank you for the Node.js SDK. We do have a few questions that we'll run through with a couple of minutes that we have remaining. And first up is, how much does the new streamlined architecture improve the eventually consistent latencies?
I don't know because I never did any tests on what eventual consistency kind of windows there were previously. So it's currently unknown as far as I know.
All right. Well, leaving opportunity for someone to explore and venture out for us, right?
Exactly.
All right. Next up, are there any mechanisms in which we can abandon the process instance creation while there is significant backpressure?
Yes, you can. Yeah, all of the in-flight requests are abortable in this new SDK.
Fantastic. Next up, are the samples that you shared today also available in Java?
Not yet, no. I mean, you can build all of the stuff yourself, but with the SDKs, we're building it in a way where it's just built in for you. So it's not IKEA where you have to kind of assemble it yourself, but we're not there with the Java one yet.
Okay. Moving on, will the new test framework help with some of these challenges?
Not yet, no, because the new test framework is designed to test the logic of the process rather than the performance. So eventual consistency, you'll run something and it will work 100% of the time in development, and then it goes into deployment and it works until it doesn't, and then it fails 3% of the time and you don't know why.
Excellent. And then I think this is the last one because we have two here and one looks like a duplicate. Can you recommend a JavaScript or a Java library or programming patterns to help work around some of these distributed system challenges?
Well, you could try the Camunda 8 Node.js SDK.
Excellent.
Just to pitch it. I think in Java there's one called Awaitable. Yeah, but we really want to build this into the system so that you don't have to think about these kind of things. We can centralize the knowledge and experience around that and then put it into a reproducible form for you.
Fantastic. Well, Josh, thank you so much.
Appreciate
it.